Now let's discuss the NVM API configuration class 1 separately. So what is the specialty of NVM configuration class 1? The important feature of this configuration class is that it provides a minimum set of API calls. Okay, so it's basic set of APIs are given. So we don't have some extended features or the full functionality that could be given by AutoSAR. We are not using. We have some basic features. And this is important. For example, there are hardwares which have limited memory and those kind of stiff requirements. So in those scenarios, we can't have all those extra functionalities if we are not going to use them. So in such cases, we can go for NVM API configuration class 1. Now, in this case, we will not support any immediate data to be written. So what do we mean by immediate data? So if we are trying to, there are two ways we can store information. One is immediately, or the second one is deferred. So if we want to store the immediately, we have to update the value to the NV block. Then we have to go for the immediate data transfer. Otherwise, we have to go for the deferred. So in that case, maybe for example, NVM write all, which is called at the shutdown phase. At that time, maybe we can update the value. So that's the two kind of data how we can store. So in this configuration class, we are not supporting the immediate data. Now the API called NVM set RAM block status that we have actually discussed briefly is only available if we configure it by the API by setting the configuration parameter NVM set RAM block status API. Okay, so to get this API in this configuration class, we have to enable this configuration parameter. Now within API configuration class 1, the block management type NVM block dataset is not supported. So we will not be able to use the NVM block dataset type when we are only having the configuration class 1 with us. So now let's look at the different APIs that are available in this configuration class. So as you can see in this table, I have divided all these depending on their types. And as you can see, there are say six different APIs we are able to get. And two of them are in type 1 and three of them are in type 3, and finally one of the API is available in type 4. Let's try to understand each of these APIs now. NVM get error status. So it has two arguments. One is the block ID and one is the request result pointer. Now this is a service or an API which is used to read the block dependent error status information. So if you remember, in the admin block, we are storing the error or status information. So if you want to get that data, so while we are running, then we can get that data by using this API. We will call this API, we will pass this block ID and this request result pointer, and then we will be able to get the or read the block dependent error status. Now this is a synchronous API and it's of type 1. Now it provides block specific error status information in the admin block of NVRAM block. That's what I just mentioned. It will provide us the error status information which is in the admin block of the NVRAM block. Now the status can be set by a previous or current asynchronous request. Okay, the status that we are reading could have been set by either a previous or a current asynchronous request. Now the request result pointer is the pointer where the requested result is available. Okay, so this is the pointer which we'll use to get the requested result. And block ID is basically the ID of the block which we are trying to get the status information. So that's what is mentioned about the arguments that we are passing or the parameters that we call with this API. Next, we have a NVM set RAM block status API. So we have seen this API before. It was used for the different actions while we are going for shutdown and startup. We are using this to set the RAM block status. Again, RAM block status is a topic we'll be discussing after we finish the APIs. So let's look at NVM set RAM block status, what it does. It is used for setting the RAM block state of an NVRAM block. So simply put, this will let us set the state of a RAM block, NVRAM block. Now it is only applicable if permanent RAM block is configured. We can't use this API for a temporary RAM block. Now what is the difference between a permanent RAM block and a temporary RAM block? So for permanent RAM block, there will be specific address and the location will be defined for it. So in that particular location, we will be only using for storing that particular data. Okay, but in case of a temporary RAM block, we don't have this function. We will be using a shared pool of data. So many different software components can use the same RAM block for storing different values, and it's temporary in nature. But if you use the permanent RAM block, it's always used by the one software component or somebody for getting a particular value at a particular address. So only this value will be stored in this particular address, and that's why we are calling it permanent. Okay, because at the entire runtime we are using this RAM block for that specific value or at that specific address. So if we want to use this API, we have the restriction that we can only have permanent RAM blocks. Okay, we cannot use this API for a temporary RAM block. Now it's of a synchronous API. It's a synchronous API and it's of type 1 category. The block ID here will help us to recognize which is the NVM block descriptor. Okay, so what is NVM block descriptor is also, this is a new term. So I'll just briefly explain what is NVM block descriptor. So if you remember, the NVRAM actually composed of different modules, right? Or different parts, right? The RAM block, the ROM block, admin block. So all those parameter or all those configurations that are required to identify one particular block in memory in the NVM, that is what is called as NVM block descriptor. So it's basically a block which gives us all the information about that particular block. Okay, so let's say block A, then we get to describe that block. What is its type? What does it support CRC? Does it have some init callbacks? So all these parameters for one block we can describe in a block descriptor, and this is used to identify, or it is used to explain what each NVRAM block. So each NVRAM block will have its own NVM block descriptor. So back again, block ID will help us to recognize the NVM block descriptor. I think that's clear. Now block change is used to validate RAM block and mark as unchanged or changed. Okay, so we'll be able to validate the RAM block, and if it is changed or unchanged, we can actually we can mark that. Okay, so block change is used to validate and just know if the value is changed or unchanged. So if we want to say set the block as changed, we can actually use this API. Give the block ID, mark it as changed as parameter, and then it will update that RAM block status accordingly. Now let's come to one of the most important APIs that we'll need to learn, which is NVM read all. Again, this API we had come across before, but we couldn't go in much detail. But now we will go in detail to this. So basically, NVM read all is a multi-block read request. It is used to read multiple blocks at a time. It is an asynchronous API and it's of type 3. It basically provides two functions. First function, it is that it initializes the management data for all the NVRAM blocks. The second one is that it will copy the data to permanent RAM block for the configured NVRAM block. So if we say, for example, these set of blocks need to be read every time the ECU starts up. So we will mark it for NVM read all, and those will be copied to the permanent RAM block from NV block once the ECU starts. So just remember that, how it is happening. And another property is that it initializes the management data. Okay, whatever management data is there, that is also initialized by this NVM read all API. Now, this API may be triggered only by the ECU state manager or ECUM at system startup. So it is the duty of the ECUM to call this at the system startup. No other module is doing this. We have to use the ECM, and it is ECM's responsibility to call this API at the startup phase. Now, NVM read all shall validate the configuration ID by compare the stored configuration ID. So if you remember when we described the dynamic configuration, we mentioned that at the starting time we will be checking if the dynamic configuration value, right, is it true or false. So if it is false, we will not use the comparison mechanism. But if it is true, okay, then we have to do the validation procedure. So this is done at the time of NVM read all. Now, if the configuration ID is mismatched, but we have set the parameter of dynamic configuration as false, we don't need to care if the configuration ID is mismatched. So we shall ignore the configuration ID in this case. Now, NVM read all shall process only the permanent RAM blocks which are configured with NVM select block for read all parameter as true. So this is a parameter for each NVM block descriptor. We'll have this parameter which is NVM select block for read all. So if we check this parameter, that means for this particular block, we'll read the value from NV memory once the ECU starts up. Okay. Okay, let's go to the next one. Now, if configured by NVM driver mode switch or DRV mode switch, this is another parameter for NVM read all. If we use this, we will have some functionality to increase or decrease the speed at which this process is taking place. So for example, we can use the memory device to read it faster during startup time. So some projects have some memory requirements or the starting time requirements. We need to start up in this much amount of time. So at that time, we need if we need to adhere to it, we need to go fast mode, for example. So if we use this fast mode, which is actually something supported by the lower layer. So that's what we need to check first. So if we have the support, we can use this fast feature to increase or make it faster at the startup time, because we are reading a lot of blocks, right? If we read a lot of blocks at the same time, it will take, it's reading from memory, so it will take some time. So depending on our requirement, we can switch the driver mode to fast or slow mode. So this is a configuration parameter. Now, NVM read all shall load the default values to the RAM block according to processing of the NVM restore block defaults. So if, for example, if the CRC calculation is configured and if the calculated CRC is not matching, then by processing the NVM restore block defaults, okay, we will be able to load the default values, okay, if there is some mismatch. So that is about the restoring block defaults when the CRC is not matching. This is all happening at the NVM read all time. Now, if there are no default values available, then the job shall leave the RAM block invalid. So it will set the RAM block as invalid. Okay. Now, if configured by NVM single block callback, the job of the function NVM read all shall call the single block callback. So what does this mean? So for example, we'll be able to assign single block callbacks for each of the NV block or the NVRAM block descriptors. So for each of them, we will be able to assign a single block callback. So once it is processed, this callback will be called. So suppose we have block A, block B, block C. For each of them, we can specifically configure callbacks. And so once NVM read all is taking place, once one of this block is read, we can get the callback called for that particular block. The idea behind using this approach is that for this single block callbacks is that it will speed up the software initialization process. So for example, if RTA, which will be needing this data, right? If it is some values read. So using immediate notification from one of the block, RT can start initializing that particular module. So if there is a module A which depends on, which is present in RT, and it is depending on in reading of the data in B. Okay, that is B memory. So once B memory is initialized during read all, we can actually set an event, for example, so that RT is notified this value is read, and this is notified using the callback. Okay, so that's what I'm saying here. A single block callback is issued from multi-block request will result in an RT event. So using these events, we can actually make the initialization process faster. So once one block is read, we can give the callback for that. So if somebody needs to act on it immediately. Okay. So that's all about NVM read all. Now we will discuss another important topic, which is the NVM write all. So in this API, it is a multi-block write request. Till it is used to write multiple blocks. It's an asynchronous API of type 3, and it is used for synchronizing the contents of permanent rank blocks to the corresponding NV blocks. And when it takes place during the shutdown. So for example, the software is up, NVM read all is performed, values read to the memory. Now the software is running normally. Now we go to shutdown after doing some changes in the values of some variables, and these are updated in permanent RAM blocks. So now once we are going to shut down, we need to store this permanent RAM block value somewhere, right? So that time we will call the NVM write all during shutdown phase. And this will help us to store these values into the corresponding NV blocks. Now this request must only be triggered by the ECU state manager and at the shutdown of the system. So again, as we saw in NVM read all, ECUM or the ECU state manager is in charge of calling these two APIs, namely the NVM read all and the NVM write all. So even during the shutdown, it is duty of ECUM to call the NVM write all API and thereby write all the updated permanent RAM block value to the NV block. Now the job of the function NVM write all shall process all permanent RAM block except for block ID 0. Okay, so the NVM write all will perform the writing for all RAM blocks except the block ID 0. If you remember, block ID 0 is reserved, right? Yeah. So that's about the block ID 0. Now, if configured by again we have the same parameter we saw, the NVM driver mode switch. If this is used, we can actually use the fast or slow mode. If it is supported by the underlying layer, we can use this to increase the speed at which the memory is written. So that can make our execution faster. Another important thing we need to be careful in this API is the write protection. So when we discuss the write protection feature, right, we can actually protect the memory from being overwritten by setting one parameter. So it is the duty of NVM write all to check if the protection state of the RAM block in advance. Okay, so that is important. We need to check before trying to write something. Now NVM write all may write unchanged data. Okay, if this would require NV data, otherwise it should not write unchanged data. So this is obvious, right? I mean, if the value has not changed, why should we waste a write cycle by writing the same data? But for example, if there is some repair work, there is some values redundant or lost or something, that time we have to definitely update because we have some issue there. But otherwise, it should not actually write the unchanged data. Now, NVM write all shall check the number of write retries by a write retry counter. So if it's trying to write, sometimes it fails, right? So if at each unsuccessful attempt, it will update a counter, and we can actually set the counter value also in configuration. How many times we want the system to retry this writing to the NVMe memory. Now, if NVMe write all has successfully written data to NVMe memory for a NVMe RAM block, with NVM write block once equal to see another parameter is coming place. It is coming here, which is the NVM write block once. So as you can see from the name itself, it is like it should be only written once. Okay. So now, for example, NVM write all first time it is doing this, it is updating, and the parameter is write block once is true. Now we will immediately set the corresponding write protection flag for this block in the admin block. So next time we will not try to write again into this block because it has been written once. But for the first time, we will be successfully writing. Second time, before that, we will have already set the write protection flag. So no further updation will happen. Now, NVM write also shall request a CRC recalculation. So, for example, if the values actually change, right, then the new CRC needs to be calculated and stored for each RAM block, for example. So, this recalculation will be initiated by NVM write all. Okay. Suppose if CRC is configured for this NVRAM, okay, so if that is a condition also, right? If CRC is not configured, then we will not initiate this recalculation. So if CRC is configured for this NVRAM block, then we will during NVRAM write all a request for a CRC recalculation will be done. Now again, we will not be writing all RAM blocks. Okay, we will be only processing those RAM blocks in which we have configured it for the NVM select block for write all. Okay, so again we'll be able to check this for each block separately, which all blocks need to be written. We can specifically check those blocks. So that's all about the NVM write all. And these two APIs we discussed, NVM read all and write all, is the most important APIs that you should be familiar with. Now we'll discuss the API NVM cancel write all. So NVM cancel write all is a service or API used to cancel a running NVM write all request. So for example, we have initiated, the ECM has initiated the NVM write all. But suppose we want to cancel that due to some condition, something that happened, could be any requirement. So at that time, we will call the NVM cancel write all. And it will cancel the current running NVM write all operation. No effect occurs if no NVM write all. So if this API is called when NVM write all is not executing, we will not see an effect. This is an API that's used to interrupt NVM write all. Okay. Now it's an asynchronous API. It's of type 3 category. So even if we terminate the NVM write all, we will not compromise on the data consistency. Okay. It's not like we'll interrupt the writing process and put some dummy value or something. The termination will be done with no compromise on the data consistency. And another point is that it will not modify any management information. So any kind of management information that is there will not be compromised by a call of NVM cancel write all. And if we perform multiple NVM cancel write all, we are calling it multiple times, then it will be treated as a single request. So ultimately we have already sent one request. So if we call it multiple times, it will be treated as a single request. Now the next API is NVM init. This API is used for resetting all the internal variables, for example, queues, state machines, etc., to the initial values. So that's the purpose. When we call NVM init at the start, it is what it is doing is that it is resetting all the flags, queues, state machines, etc., to the initial values. It's a synchronous API of type 4 category. Now, once this is called, it will also set the dataset index of all dataset NVRAM blocks to 0. So if there are multiple datasets, all the index of these datasets are initialized to 0 in the call of NVM init. Now just remember that the initialization of RAM data blocks shall be done by another request, which is the NVM reader. We are not initializing the RAM block. The RAM blocks are initialized by the call of NVM read all. Here we are just doing the initial steps like resetting the queue, state machines, flags, etc. So that's all about the NVM configuration class 1 APIs. In the next lecture, we will discuss the configuration class 2.